Let's take an example to see how we can use the conservation of mass, conservation of energy, entropy balance with the definition of thermal isentropic efficiency to solve this example. This example says we have ammonia. This ammonia enters an adiabatic. So this word adiabatic means Q is 0. Steady state. So this means any accumulation term, this will be 0. A compressor. This compressor, the inlet at 20 kilopascal, the outlet at 300 Kelvin. So this is the inlet, 20 kilopascal. This is the inlet temperature, 300 Kelvin. And it leaves at 0.1 megapascal. So this is the outlet, 0.1 megapascal. Just when you start, if you need to convert everything from SI, for example, just make sure that here the inlet pressure is kilopascal, here the outlet pressure is megapascal. So kilopascal, this one, to convert it to pascal, so you can say the inlet pressure, this is 20 times 10 to the power 3 pascal. Megapascal, to convert it to pascal, so this one, so we have the pressure out, this one will be 0.1 times 2 to the power 6 pascal. So because here we have kilopascal, we multiply by 10 to the power 3, megapascal, here we multiply by 10 to the power 6. Ammonia can be assumed as an ideal gas at this condition. The compressor efficiency is 75%. So this is thermal efficiency or isentropic efficiency. Is this something for a whole heat engine or just a single component? Single component, right? So this is single component. So this one or this efficiency here, this is isentropic efficiency. And isentropic efficiency for compressor, so this one will be work reversible divided by work irreversible. Because compressor, it's work, use work as an input. Okay, so for this one, for the compressor work as an input, so this one will be work theoretical divided by work actual. Okay, clear? Okay. So we have two things. We need to calculate the amount of work required for each mole of gas compressor. So if we have 1 mole of this gas, what will be the amount of work required to compress just 1 mole of this gas? And what is the temperature of the outgoing gas? So in order to solve this example, then we need to calculate work, we need to calculate temperature, then so what is the equation that contains work? So we have conservation of mass. Okay, it says input mass equal output mass. This example says we have a steady state, so there is no mass change. So whatever inlet mass is equivalent to the outlet mass, or the inlet number of moles is equivalent to the outlet number of moles. This is what we need to understand from the conservation of mass. Then we have the first law of thermodynamics. So from the first law of thermodynamics, what we have accumulation term equal the inlet mass flow rate times specific enthalpy plus GH plus V square over 2, and all of this for the inlets, minus the outlet mass flow rate of the outlet times specific enthalpy plus GH plus V square over 2 of the outlet. Why in this first law of thermodynamics? If you remember, first law of thermodynamics has two forms. One contains internal energy, another one contains enthalpy, right? So why here I picked the one that contains enthalpy, not internal energy? You remember the difference between them? Internal energy, this is for closed system. For open system, we have internal energy, we have flow work. So we combine both terms together in enthalpy. So here in this example, we have inlet, we have outlet. So this is an example of open system. So we have internal energy, we have flow work. So this is why we have enthalpy. Just instead of using two terms, just one term is enough. So we have this term plus Q plus work of expansion contraction plus shaft work. This is the whole formula we have for the first law of thermodynamics. We remember that from the conservation of mass, inlet mass flow rate, outlet mass flow rate, these two will be the same. Same inlet, same outlet. So you can, instead of saying inlet mass flow rate, outlet mass flow rate, we just can say M lot because it had the same number. For the other terms, this process is a steady state. This is given. So the accumulation will be 0. Inlet and outlet at the same horizontal level. So this potential term will be cancelled with this potential term. The example that I mentioned, any change in the diameter of the inlet pipe or the diameter of the outlet pipe. So the kinetic energy will be cancelled. It's also given the process is adiabatic, so there is no Q. There is no piston causing any expansion or contraction, so there is no expansion or contraction. So now this equation here, we can rewrite it in this way. We can say then shaft work divided by mass flow rate. This will be equivalent to the enthalpy of the outlet minus enthalpy of the inlet. Clear? Any questions so far? Okay. But we need to know that here in the requirement, it's required to calculate shaft work to compress one mole. So in the requirements, if you get back to the problem, it said we need to find the work required for each 1 mole. So we're just telling you here in the requirements, this is the amount of work per unit mass. Here we have the specific enthalpy of the outlet, specific enthalpy of the inlet. So instead of using like everything divided by mass, instead of using the specific properties, convert everything to mole basis. So according to this one, we can have the same equation. Shaft work divided by moles equal molar enthalpy of the outlet minus molar enthalpy of the inlet. Just to be consistent with the requirement we have here. So far it's clear? So this is the first requirement. What is the shaft work we have in this example? Because this is ammonia, this is not steam, so we can't use the steam tables. But he said in the problem, we can assume ideal gas behavior. So we know that since we have ideal gas, then we can say dH equal Cp dt, the equation that we can use to calculate the change we have in the enthalpy for ideal gas. Okay. So let's assume that now let's assume we have Cp of ammonia this one is equivalent to like 25, or let's do it this way. This is equivalent to parameter A, which is 25.235 and the units we have is joule per minute. So assume this is CP we have, so which means we have this CP is constant. So if we have this case, CP equal this number, CP of ammonia is constant, then we can integrate DH equation. So we can say by integration, then delta H, which is molar enthalpy outlet minus molar enthalpy of the inlet. This one will be N CP delta T, which will be N CP. There is no N because it's smaller. This one will be CP T2 minus T1. CP is known. I know the value of CP, which is 25.235. T1 is also known. This one is given 300 Kelvin. But T2, this is not known here. So I don't know the value of T2 I have here in this example. So this is why I have problem in calculating the this temperature we have here in this example. So what we need to do in this one, we need to find a way to calculate the outlet temperature. We need a way to calculate this temperature. Okay. So what else we can do in this example? So the other thing that we need, in this example he said we have like steady state process, we have adiabatic process. So we have ideal gas with constant heat capacity. So if you remember from last week we said we have equations to calculate the entropy if we have ideal gas with constant heat capacity. We said one of them looks like this equation. So we have ideal gas with constant heat capacity so we know that the change we have in the molar enthalpy, this one is CV then T2 over T1 plus R then V2 over V1. So this is an equation we explained just 2 lectures. We have some equations to calculate the entropy change if we have ideal gas with constant heat capacity. So this equation contains the parameter that we need to find, which is T2. We have this missing parameter that we can need to find. But what else we have in this equation? So we have T1, this is 300. We have CV, we can find, because we know that for ideal gas, CP is CV plus R. So we can say CV, this one will be CP 5.235 minus 8.314. So we have the value of CV, This is fine. Then we can have the molar volume. Okay, we have ideal gas, so we can say V2, this is RT over P. So this one will be R divided by outlet temperature over outlet pressure from the ideal gas equation of the states. Molar volume at the inlet, this is R inlet temperature divided by inlet pressure. So with the value of R is known, the value of T2, this is unknown. Still, I have this value is unknown here. The value of the outlet pressure, this one is known. T1 is known, P1 is known. So we have this equation. How many unknowns do we have in this equation so far? 2. The value of the outlet temperature, which if we can find this value, then we can substitute in enthalpy equation, calculate enthalpy, then calculate work. And this is what we need to find. But here we have one more thing that is also missing, which is the entropy change. This is also missing. And we have no idea what is the entropy change for this process. But if we assume we have a reversible process. And at the same time, it's given that we have an adiabatic process. So we have reversible process, we have adiabatic process. These two words together equivalent to what? Isentropic, yes. An isentropic means the change we have in the entropy is equivalent to 0. So now we can substitute in the entropy change equation. So now we can substitute in delta S equation. So now everything is known except the outlet temperature. So now if we substitute in this one, then we can say the outlet temperature T2, this one will be equivalent to 4 to 8.7 Kelvin. But again, this is not the actual outlet temperature. This is the outlet temperature for a reversible process. Now we can use this temperature that we have for the outlet system. So now we can substitute in delta H equation that we have delta H is Cp T2 minus T1. We have Cp, we have inlet temperature, and we have the outlet temperature if the process is reversible. So we can substitute in this equation, and we can say that then delta H will be 4.839 joule per mole. Again, this one for a reversible process. So now take this delta H enthalpy change and substitute in this equation the first law of thermodynamics to calculate the shaft work. So now substitute in the first law of thermodynamics and then we can say the shaft work divided by number of moles. This one will be 4,839 joule per mole. But again, this one is for a reversible process. So now I calculated the shaft work, I calculated temperature. These are the two requirements. The requirements: calculate the shaft work, calculate the temperature. But both of them I calculated based on assumption that the process is reversible. This is not the actual process. This is not the actual amount of work needed. This is not the actual temperature. So how we can change everything to the actual condition? There is one thing missing that we didn't use. Do you remember the isentropic efficiency? Okay. So we have here given, this one was given, that the efficiency of this compressor is 75%. So we can say for this one 0.75 equal the shaft work reversible divided by shaft work irreversible. And what is the shaft work reversible? This is what we calculated here, 4,839. So just by using this efficiency, we can substitute in it, and then we have the shaft work divided by 1 mole. So this one will be 600,452 joule per mole. And this is the first requirement that we have in this problem. Clear? Then we need to calculate the outlet temperature. So now we have the shaft work. So if we substitute with this new value in first law of thermodynamics, so we will have delta H. This one also will be 6,452 joule per mole, and delta H is Cp T2 minus T1. So now we have the value of Cp. This one is given 25.253. We have T1 is given 300. I substitute with the actual enthalpy change, not the theoretical one. So now I can calculate the outlet temperature, and the actual outlet temperature we have here in this example will be 468.8 Kelvin, and this is the requirements we have. So here in this example, just you can see we have 4 temperatures, we have 4 pressures. This is the outlet temperature if the process is reversible, if the process is ideal. But now this is the outlet temperature for our real process. For the shaft work, so we have here, this is the shaft work, input shaft work, 4,800. This is the ideal, or this is the minimum shaft work needed for this device. But actually, you will not give the device 4,800, you will give it 6,452. This is the actual amount of work needed as an input for this device.